Is Kevin inside? Jerry, do you know the Kevin is inside? Hey, Jerry. Jerry, can you help me? Can you help me?啊？那个 host 的 email 是哪一个？happened? Jerry, did you send the wrong email to them or what? What happened? Jerry. Yeah, I can hear you, but you need to let the speaker to come in. Okay, I think sorry for that. I think there's some technical issues. And Kevin, can you hear me? But I think can you hear me? Kevin, can you hear me? I think I cannot hear you, Kevin. Kevin is unmuted or what? 那个 Jerry, the Kevin is muted. I think Kevin, you made it get out and go inside again. No, I think we cannot hear you. I'm sorry, we are a little bit delayed because of some technical issues. Kevin, can you hear us? Hello? Can you share your screen? Kevin, can you share screen? You don't need to, yeah.
Can you hear me?
Yeah, now it's okay. I think I need to introduce you first.
Excellent.
Can you hear
Thank
us?
you.
Okay.
Yes.
Okay. Good morning and a good night, everyone. And it's a great pleasure to introduce today's speaker, and Professor Kevin Zhou. And actually, Professor Kevin Zhou obtained his PhD degree from the University of Maryland, College Park. Now he's a professor and the executive dean of School of Biomedical Engineering, Shenzhen University Institute for Advanced Research, University of Science and Technology of China, and adjunct professor at the Institute of the Computing Technology, Chinese Academy of Science and Chinese University of Hong Kong, Shenzhen. And prior to this, and he's a principal expert and the senior R&D director at the Siemens Healthcare Research. Dr. Zhou has published over 240 papers, books, chapters, and peer-reviewed papers, journals, and conference papers, and registered over 140 granted patents. That's very impressive, and written two research books and edited 3 books. And actually, he has won multiple awards, including R&D 100 awards, and the Siemens Inventor of the Year, and the UMDEC Distinguished Alumni Award. He has been a program co-chair for MICCAI 2020, an editor and board member for IEEE Medical Image and Medical Image Analysis. And I think welcome, Kevin. It's your turn.
Thank you. Thank you so much. Thanks for your nice introduction. And I'm very happy to have this golden opportunity for me to share some of my thoughts and my work on medical image analysis. So as you can see, my title is about traits and the trends of AI in medical imaging. So the first question I want to try to answer is, what is medical imaging, or what are the special distinct properties or features of medical imaging? So this is about the imaging traits. So I'm going to summarize the traits from these 7 elements. The first one is about image itself, and we all know that medical image has multiple modalities, right? On the screen, you can see X-ray, MRI, PET, and ultrasound, and the CT. And the image of the CT doesn't look like CT in a normal way. However, it's because the CT modality itself is of high resolution. So with such a high resolution CT, now you can use like modern rendering technology, and rendered image looks like a picture. So that's the second property here. Actually, a sub property is like each modality, the resolution is going higher and higher. All right. Now another part is regarding the data. Unfortunately, there are many different machines, and each machine are used in hospitals. They all have like specific protocols and so on. So that creates a non-standard acquisition situation. So in the way that even though it's the same patient, but if you go to different sites, you get different look, right? So that creates a problem basically. In particular, it basically means like the model you trained from the data at sites A and B, if you use the data at site C, the model might fail, right? So that's a typical issue. Another issue is like we do have a lot of data. However, all these data are scattered around, isolated. They are not centralized or cannot be used in a coherent way. So that's another problem, right? So how to use this non-stat data and isolate data, it becomes a technical challenge. And another part is we know that image is essentially is a phenotype of disease. We try to find disease or cure disease or whatever, find this basically, find something related about disease from the images, right? So we have to look at the disease space. And if you look at this famous knowledge base called cancer radiology gametes, it defines the sort of some kind of keywords or some disease or some symptoms of the disease and so on. And it's a huge, it defines a huge number of items, right? It's have almost like 70,000 items. So which is a big knowledge space, as you can see. And another issue is like when we have so many, each item you can think of the disease or a specific description of disease. So if we look at then the prevalence of this, right? It is unfortunately you have a typical long tail. So in the sense that there's a small amount of disease, it actually occupies a large amount of data. So these are, as we know, it's a common disease, right? And however, there's a large amount of disease which has a very few amount of data. So we from like they actually try to look at different anatomic regions, right? The head, the brain, the breast, the abdominal, the cardiovascular. And then when you combine all this, right, with you have so many tasks, you have so many modalities, so many anatomic regions, and so on, so many disease and all this. So it's a huge problem space, basically. So it's a very complex and diverse. And then further, if you look at another security issue, so this is in terms of the attack, right? So the AI models is actually fragile and unstable. If you add some imperceptible noise on top of the image, you can actually manipulate the, in this case, the landmark detect module to output the landmark locations at arbitrary positions. So this is known that this adversarial attack issue. And we recently actually showed that for AI images, when it compares, for medical imaging, when it compare with natural images, this is even more vulnerable, and you can actually attack a medical AI model with much light perturbation. All right, so these are the sort of the distinct features related to medical imaging. And from that, if we look at all the publications, and more or less they are actually try to address some part of these issues or leveraging this distinct properties to solve for specific medical image analysis task or challenge. All right, and this sort of defines the trends of the current medical image analysis literature. If you want to dig into more, right? So today I'm going to show, I'm not able to cover everything, obviously. So I'm going to mainly show some of my work around these lines. And if you are interested in the quick grasp of what's going on, so you can look at these two survey papers we recently wrote. One is on a review of deep learning in medical imaging. Another is a review of deep reinforcement learning in medical imaging. And these two papers will give you a rather comprehensive ideas of what's going on, as well as the traits and the training algorithms in the literature. Today, I'm going to talk about some of my research around these lines. So one particular thing, we all know that if we have a task, right, say CT lung nodule segmentation or detection. So this is a very specific task. And if we are able to accumulate a large number of training data, so in the sense, I call it small task and big data. And in this particular setting, and we are able to train a rather deep network, and more or less the performance is a phenomenon, right? We know that we all hear about all this superhuman performance is all coming from this kind of scenario. However, the reality is rather challenging, right? So as I argued, in reality, we have many different tasks, and for each task, we don't have a lot of data. So instead, we have to deal with big tasks and small data. And that is, to me, is the challenge we have to deal with in order to push the research to the next level, right? And so this is essential problem, I would say, sort of almost the holy grail we want to address in medical image analysis. And how can we approach this, right? So this is obviously challenging. We have maybe 10,000 tasks, right? Or even more than that, actually. And each task, we don't have a lot of data. So what should we do? So I'm going to actually talk about three approach towards big task and small data. And one particular approach is reducing the amount of labels, right? So we, instead of small task, big data, so how about we start with small task, small data, right? And then we just add more tasks. So that is possible way to reach big task, small data, right? So that's one way. Now, the second way I'm going to talk about is called building a universal model, in the way that we do have already, we have a lot of tasks, right? And each task we have data. So what if we are able to build a universal model instead of building individualized model? And that way we can pull the data together, and we can possibly get a better performance. And the third line of research is how to fuse the domain knowledge with with machine learning or deep learning, so that we can try to achieve big tasks and small data. So the first is reducing amount of labels. So I'm going to show you some examples. Quite a phenomenon, as you can see, right? If you only train for this multi-class, you have 30 labels, and if you train a model, the average dice is 87. Okay. Now, if you can also train a binary organ classifier, say you have a liver segmentation model, you have a pancreas segmentation, all separate, right? And that way, you go train 4 different models. In this case, the kidney, there are 2 kidneys, but we train 1 model. And that the dice is 85%. And if we use our we call this marginal loss, right? Which we are able to leverage all existing data. And then all of a sudden, we boost the performance to the dice is increased to 93. So this is really almost like free lunch, right? The only thing is like you just integrate all together. So that's one way. All right. Now let's look at another typical trick nowadays is very popular, is self-supervised learning. So in this is leveraging this large amount unlabeled images, while for the target task, we only have a few labeled data, right? So from unlabeled images, we define a proxy task. From that, we can train a network and create a pre-trained model. And then we sort of use that to initialize the actual model we want to learn. And this is for the target task. And we fine tune this model with this label data. and get the final target model. So this is a very typical self-supervised learning framework. And we are among those who actually try to introduce self-supervised learning for medical image analysis, rather like early groups. And we introduce this Rubik's Cube idea. And this is rather trivial in the way that you break an image into 8 small patch, right? And then a 3D patch, and then you can rotate them and rearrange them, whatever, and create a proxy task and learn that. And with that, we're able to show that if we compare with the train from the scratch, meaning you only train with a few training labels, and that creates a big, typically creates a big overfitting issue, and the performance is not good. And with this self-supervised Rubik's Cube learning, and you can boost the results of hemorrhage detection. And the same for MR brain region segmentation, and you got a nice 6% boost in terms of dice. Okay, now, so this is like in the case that you have only a few labeled images, right? So you have a large number of unlabeled images and with a few labeled image. So how about we push this to further to another extreme, right? We only have one label, a one shot, right? So we started this scenario in landmark detection. In this case, we have an image. We want to detect 19 landmarks associated with the CT head image, and these landmarks are detected because surgeons want to use them to plan the surgery of the plan the surgery basically. So the situation statistics. So this is quite amazing, as you can see. So our one label, right, with only one label, we're able to match the performance in between 10 to 25. It's about actually 20 labels. So this is like how this one-shot detection can achieve. And we are, in fact, further look at this particular interesting question, like which image to label, right? If you recall here, so we have a template selection issue because we really don't know which template is the best one, right? Unless we look at the test error of using each template, and we know the best one. So we want to find the template, and so that it can close to the sort of the best template. So this is like what we want to do, right? Which image to label. And here you can see this is sort of the MRG error using all templates, right? Like we can exhaustively using all the images as template and report the error. And you can see the error actually varies quite a lot, right? From 2.9 to 4.4. And this error is actually tested, is produced based on the training data. So therefore it doesn't match the number here. But more or less you can see the diverse, right? So the template choice matters a lot, right? If you pick a template here, and then the error will be slow. Error will be low, right? Otherwise, error could be as high as 4.4. So we try to find the solutions to find this picture, so that we want to find the template, and ideally here, and then we can reduce the final MRE. And this is actually what we did. We designed a sample choice policy, try to find that. So the main idea is, in this case, we actually have no idea which landmarks, because we haven't even annotated, right? So we start with just the image, and then we designed an approach which is essentially using general purpose key points as a surrogate of the landmarks, and then use that to find the sort of the average, the best template. And this is what we do, right? As you can see, using our approach, we are able to find a template. The MRG is 2.7, and the sort of the best template is 2.6. So we are able to do something around these lines and find a rather good image to begin with to label it. All right, and we actually further push this label idea. So we studied the called label-free COVID-19 segmentation. So this is like really the real research happens in 2020. So when the COVID just started, we don't have a lot of data. So we decided to do something. So we started to do a label-free. So without any COVID-19 lesion segmentation, we are able to train a model for segmentation, right? So the whole idea is rather simple. We designed a certain models to create a synthetic lesion. So as you can see, this model is very simple. It actually consists of simple operations like create a noise image, then filter it, and then scale it, and then use again to derive it, and create another noise image, filter it, and scale it. And then We design its own parameters, right? W1, which is really like a blade, right, for this task. And then we combine it together, it forms its own specific network, have W0, WT, and output the Y, right? And the same for the second pass and for the T task. This is a very simple design. And with this design, the nice thing about this design is like the base part, as you can see, right? It essentially see all the data. So therefore the base is really, really robust, right? So, and then the blade is very sort of like customized, specific to the task. So it kind of fine tune the overall model to fit the task. And this is this is a rather simple idea, right? And in practice, you can design a very specific variants of this kind of model. You can fit with convolutional neural network. You can use transformer, whatever Schwer model. And if you can use this kind of design, right? Maybe you use, say, all these parameters for your say in your batch normalization layer, whatever, you can basically, use your own creativity and design your network for your task, right? And I'm going to show some examples. So the first example is, this is paper published in last year, MICCAI. What we have is like 3 different tasks, right? So we have 3 different X-ray images, and from all these images, 1 to 2 landmarks. And the conventional wisdom is like, oh, I'm going to train the collect data for each task and the train 3 different model, right? So that's what typically people will do. And then there's also like SOTA models for each different anatomical regions. And we designed a Swiss knife kind of model, a universal model. And this is approach. This is a performance we can achieve. We call it a GU2net. And this is the SOTA model for the head, which is for this, right? This is the model, if you recall a few slides ago, I reported already. So there's the MRE and the SDR. And then with GU2net, and we are able to beat this, the state-of-art model for this particular specific task, right? And then same for the hand. And again, we, at least in terms of SDR, we are better than the state-of-the-art model, which is rather a different model from, which is rather reported in a different paper from this paper, okay? And then we have the third one, right? So again, in our model is better. So in the way, we are able to build all around the model, right? We call it universal model, and it beats actually any SOTA single task network. And this is rather amazing. It's like, you have all around the model, it actually beats individual champion, right? All right. So we did the same experiment. For a similar experiment, we built a universal undersampled MR recon model. So here the task is we want to train a universal model based on two anatomies, based on brain and the knee. So these are there are large data sets available. And the same kind of ideas we introduce, we call as being specific, which is specific for the anatomy structure. And then the other part is more or less stay the same. All right. So with that, we can actually look at the numbers. You can see. So this is the brain and knee. All right. And if we train individual modules, so for this undersampled MR reconstruction experiment, the PSNR is 40.85, right? And this is for the knee, a specific model for the knee, right? 75. And for our model, you can see we're able to actually boost the performance quite a lot. This is almost like close to 2.3 dB, right? And this is like almost 1 dB. So this is actually quite nice performance improvement in terms of reconstruction, right? And then we are also able to transfer this base model or this universal model to the unseen anatomies, right? So the idea is like we keep this base, which remember you have this common part fixed, and then we only train this its own specific part, right? And that way we can adapt our universal model to this specific anatomy. And again, you can see our model is better than individualized model. Okay, and for to train each model, we only add a few parameters because here our design, this anatomy specific model has anatomy specific part has very have a of, sort of like accrues the appearance of the lung, right? Now, so that sort of like inspires us to introduce this decomposition model, right? So what if we can decompose this model to 3 images, right? We all know that X-ray is additive imaging, right? It sort of like combines all the information around the image projection array. So if we can project this image to 3 different images, this is all the bone, right? Added together. So this is the X-ray of the bone only. This is the X-ray of the lung only, and this is the rest of the tissue. So if we can decompose this, then, right, we use them, feed this to the model, and we can get better performance because all the lung knowledge is contained in this picture, right? So this is what we did basically. We trained a decomposition network, and then get these 3 pictures, and then feed these images together into the final neural network, get the diagnosis prediction. Right? So this is our results, and the results is quite amazing. It actually improves the prediction accuracy in 11 out of 14 common lung diseases. And as a byproduct, you can see this. Oops, just 1 second. I have to. You can see this picture, which actually can sort of hide the ribs, right? Because we're able to find the rib component, so we can hide it. And you can see, once the rib is hidden, right? So you can perceive the lung part more clearly. Okay, and then we further actually did another manual comparison. This is like by reading based on 2 scenarios. Number 1 scenario is using the original image with the rib inside, and we also show the bone-free image. And then the other one is actually only using the original image. This is like the current situation, right? So we compare these 2 situations. We found that with the help of the bone-reading image, the bone-free image, the physicians can better diagnose the X-ray images, right? The accuracy goes up 8%. And further, they actually can reduce the reading time. So this is by almost 30%. The main reason is because for some images, it's actually very difficult for physicians to figure out what's going on. So those images takes a lot of time. And often for those images, with the help of the bone-free images, they are able to make the decision much more quickly. So therefore, you can see the reading time is actually reduced a lot. And if it's an easy picture, in fact, a physician can read an easy picture rather quickly. With or without the bone-free image, there's no big difference. Okay, that's the example number 1. Let's look at another example. So here the task is we take. Let me play this video. So the idea is like we take the image from the left, which is a CBCT image. It's very noisy. It's combing CT. It's very noisy. It has this sort of metal artifacts, and then you can see here, all these. This is a metal, in fact. You can see this sort of like the rays radiating out from the metal. These are called metal artifacts. And on the right-hand side, this is our metal reduced image, right? And this is the result of our method, and you can see, the metal artifacts, and the image is much reduced, and the image is less noisy. Okay, so here's our approach. We propose an artifact disentanglement network, and this is a purely unsupervised because in this metal artifacts reduction task, we cannot get a paired images, right? You can't get an image with without metal from the same patient. It's impractical to do that, and so therefore we have to do unpaired setting. So we decided to propose this ADN. So the main idea is like out of this rather looks complicated network. So we're able to learn disentanglement. It separates the contents from artifacts. All right. So this is the main network design. As you can see, this instead of a one big black box network, it has many components inside, and you piece them together to get the results. All right. And due to interest of time, I'm not able to explain the details. However, the network itself is designed based on the knowledge. And then further, we introduce multiple laws. And again, this is also based on the more and sensing device, imaging and AI, biooptics, advanced technologies. And we actually have multiple openings, and we're looking for you to join us. And thank you so much.
Okay, thank you. You have additional? Okay, I think Kevin, can you hear me?
Yes, I can hear you.
Okay, it's a very nice talk. Even the kinds of the connection is not very well, but I think I learned a lot from your presentation. And I have a, I read two of your, review papers, and I saw a lot of, I know personally I learned a lot from your reading your papers from different aspects. Yeah. And I have a couple of questions regarding to the whole field. I always have the difficulty related to when we're looking at the data, medical imaging data from more deeper perspective. A simple question like a segmentation, okay? If you really looking into like stuff like regions segmentation or some in that aspect, I didn't see a lot of progress in last 20 years, even longer. I know there's one key difficulty is because there's no ground truth, and you don't have the data to train it, and that's the kind of key bottleneck for the,
Yeah.
it's not a technology, it's not an algorithm itself.
Mm.
What do you feel about that?
It depends on, you know, which angle you want to look at the problem, right? And in one way, I agree with you, right? So definitely medical image segmentation has been for a long time, and you know, a lot of people try to do something around this, right? Around this line, and then yet the performance seems to move ahead a lot, right? Now, I try to look from different perspective, I would say. I think, you know, the reason why, first of all, right, why there are still people why are there so many people interested in medical image segmentation, right? And it's no doubt it is a clinical really important task, and that's why I think there's interest to do something around this. And then in terms of the technical advancements, right? And there I see some interesting directions. You know, one is to rather than say waiting for the large amount of annotated samples or images to be available, right? So how about we study, for example, some of the thing I'm trying to do is like one shot. Maybe say I only give you one annotation, right? I can make this annotation as accurate as I want, right? I spend a lot of money on this. That's fine. And I can also maybe curate a test data set to test this, right? And that could, you know, pose a very different challenge and open up a lot of interesting research, I would say. And basically that forces you to dig into other parts of the problem.
Okay. Another question I would love to ask is, you see that in recent years, I think the registration, because of the development of the deep learning, it seems like the registration problem is become less important in certain degree. And my understanding is correct, because for deep learning problem, because of deep learning, you don't really to align the features in a common space. Deep learning, suppose deep learning can roughly help you align all the data into the common space. And in the last layer, and in that case, for clinical application purpose, it don't seems like registration is that critically important. At least a rough kinds of registration is sufficient for most of applications. What's your feeling about that? Kevin, can you hear me? Kevin? It seems like the signal is not good. Do you wear the earphone? Yeah, I think there's some connection problems today. Yeah, you know, throughout the talk, but I think that's bad. Yeah. Maybe we just conclude the presentation today, and at the end, I would like to thank the Kevin again for giving this wonderful talk. Thank you.
Thanks so much. All right, bye-bye.